Thank you. First of all, I wish to thank Professor Bakshi and Professor Manoj Yadav for inviting me to this wonderful conference. I'm learning a lot at this conference, and particularly I wish to thank Alan Herman, with whom some of us had a very informative talk about computation of Schur indices. The Schur index was a very complex issue for us, and I think it is for many of us here also. Our interest in this talk was to compute irreducible representations of solvable groups over arbitrary fields. In the semi-simple case, that is the characteristic of the field does not divide the order of the group. Ideally, this computation means writing down matrices for the generators of the group. And the essential arithmetic of the field is factorization of cyclotomic polynomials. The Schur indices come here, but they are implicit. So this is the brief outline. The first is the introduction, then the second is the discussion of the Schur index. So Schur index has been defined for various categories now, but I wish to go back to the original definition of Schur, or when he introduced the notion. It is roughly, if you have a simple F-algebra, then its dimension over the center is a square. That's a well-known result. And the square root of that dimension is called the Schur index of that algebra. That seems a little unmotivated to me, and I would like to say something how the definition arose in the first place. Then, here G is a group, F is a field, G is a finite group, F is a field whose characteristic does not divide the order of the group. And then we introduce the notion of F-conjugacy, F-character table, and F-idempotents. Then this important theorem of Berman, who proved it in case the F is algebraically closed. And somehow we have not seen the proof of this theorem in the standard literature. The original paper is some note in Russian. So we have to decipher it, and we have to break our heads on that. And now we extend this Berman's theorem for F arbitrary, not necessarily algebraically closed. And we should illustrate this by some examples. So let me recall G a finite group, etc. Fg is the group algebra of G over F. F bar is the algebraic closure of F. V is a finite dimensional vector space over F. And V is the ring of endomorphisms of V. Aut V is the group of linear automorphisms of V. And for an irreducible F representation, rho, its corresponding primitive central idempotent in Fg, we denote it by E rho. Because the corresponding object in Fg is a minimal two-sided ideal, which is isomorphic to a matrix algebra over a division ring. And the identity element in that algebra, that is what this principal central idempotent is. So the main theory was started by Frobenius, and I browsed through the original paper of Frobenius. He is actually not talking in terms of representations as we understand today, but he introduced already characters and idempotents by their formal properties. So characters are certain functions from the group to the field, and they satisfy certain properties. This representation theoretic point of view was introduced by Schur in his thesis 6 years later, Schur was a student of Frobenius, and he handles the case F of complex numbers or an algebraically closed field of characteristic 0. But Schur clearly understood that to extend this work for the general F, there are much deeper and involved arithmetic aspects. And these arithmetic aspects, as we shall see in this development, they're just how the cyclotomic polynomials factor over the field. And in 1906, Schur wrote this paper, Arithmetische Untersuchungen, and observed most of the salient features. However, he did not have the advantage of the Witt-Berman theory, which came around in 1914, and to realize its relevance for the representation theory, it took some more years. Then Richard Brouwer in 1952 at the International Congress, he gave an account of this development in which he also removed the semi-simplicity restriction and developed this more general theory where the characteristic of the field divides the order of the group. This is the modular representation theory with which we do not deal here. So we shall first review and reformulate the works of Schur, Witt, and Berman in this case. Now, for the solvable group, there is always a normal subgroup of index P a prime. And so this is the crucial case. Then if we know the representation theory for H, then G mod H is just a cyclic group of order P. And then by combining this information, we should be able to obtain the information about the representations of G. In 1955, S.D. Berman computed, in case F is algebraically closed, a primitive central idempotent in Fg, corresponding to an irreducible F representation of G. So we extend this result when F is not algebraically, not necessarily algebraically closed. All this appears in the thesis of Soham Pradhan. As it often happens, the thesis was accepted and many results were proved there, but the better understanding arose after the thesis was accepted. So now let me recall the Schur index. So let rho be a irreducible F representation of G. The representation canonically extends to the group algebra, and let D be those endomorphisms which commute with endomorphisms of V, which commute with all rho G for G in G. And by Schur's lemma, D is a finite dimensional F algebra, which is a division ring. We call D the centralizer of G in endomorphism of V. Then Schur was interested in what happens when you tensor the representation by the algebraic closure. So Schur asserted that this tensored representation decomposes into distinct irreducible F-bar representations, rho 1, rho 2, rho k, which occur with the same multiplicity m. And that m was later called the Schur index. So this is a very concrete realization of the Schur indices arose. At the time Schur wrote the paper, I think some of the arguments are, I guess, not understood by the readers, and they became understood after the semi-simple F-algebras. That theory was developed, and after the Witt-Berman's work. And so let D be, and the only information that we need from this theory is this basic information that D be a finite dimensional F algebra, which is a division ring. Let Z be its center, Z or Z. Then Z is a finite dimensional field extension of F, and D has a structure of a Z algebra. Then the basic result is that the dimension of the division ring over its center is a square of a natural number. And then it contains maximal subfields E, which will naturally contain Z, and the maximal subfields would have dimension M over Z. And then D tensored with E over Z is isomorphic to a standard matrix algebra over the field E. And that's the split simple E algebra. And the dimension of E is the smallest dimension for which this D tensor, that field would be split. And the Schur index of D, or more generally of M and D for any n over F, may be defined to be M, as we do these days for semisimple F algebras. So the minimal two-sided ideal Fg corresponding to rho is abstractly isomorphic to the matrix ring over the division ring, and let Z be the center, and let the dimension of the center over F. So F will be contained in the center. So let that dimension be K, and E is a maximal subfield of D. Then E, of course, contains Z. Now, if you tensor Fg with Z, so we shall get the algebra over the Z group algebra of G, then it's a sum of certain number of minimal two-sided ideals, which correspond to irreducible Z representations of G. And now you see what is happening to the whole ideal. So M and D tensor Z over F is isomorphic to of course, it's a summand of the group algebra of G over Z. And since Z is the center of D, we have these isomorphisms. So M and D tensor Z over F is naturally isomorphic to M and D tensor Z over F in bracket. And this is just this dimension of Z over F is K. These are just the K copies of D additively. So this is isomorphic to the K copies of the matrix rings over D. So each of these summands is isomorphic to a minimal two-sided ideal of the group algebra ZG. And as we shall see later, this Z corresponds to the character field, as we shall see later. In terms of representations, V tensor Z splits into K many simple ZG summands, say V1 plus V2 plus Vk. Each Vi is a Z vector space, which by restriction of scalars may be regarded as an F vector space. Then this is the main number theoretic calculation. The dimension of dimension of V over F is the dimension of Z over F times the dimension of V over Z. And so this is just K M square N. So that is equal to K dimension of each Vi over Z for each I from 1 to K. Now, our irreducible representation tensored with Z splits into K distinct irreducible Z representations of G. For more precision, we shall write M and Di for the ith summand in that sum, which itself occurs as the whole thing occurs as a summand in ZG. and so each of these subsummands is isomorphic to M and D. And the corresponding representation space is Vi. Now consider Vi tensored with E. This is the maximal subfield of D. It is an E representation space of G. From the above description, its irreducible components are E representation spaces, which is isomorphic to Wi. Vi tensor Z, Vi tensor E over Z is isomorphic to Wi. And so the dimension of this Wi is over Z is nm square. And then it follows that Vi tensor E over Z is the sum of m copies of Wi. Well, this is the summary that if we start with an irreducible F representation of G and dZe as above, then V tensor E over F is this M, this each representation space W1, W2, Wk occurs m times, and it's a decomposition into distinct representation spaces, and they occur with the same multiplicity. And this was the Schur's way of thinking about what was called later the Schur Index. Now, Reiner actually gives a very different definition of Schur Index, and this is the standard definition that is used in the generalization. That if we consider F as the bottom and F bar as the top, then Reiner gives a definition of the Schur Index from the viewpoint of the top. And the fields ZE mentioned above occur as subfields of the algebraic closure, which depend on specific irreducible F representation. So it goes like this. So let rho tilde be an irreducible representation of G over F bar, and let chi be its character. Then for EG, chi G is the sum of eigenvalues of rho tilde G. Let U be the exponent of G, that is the least common multiple of the orders of elements of G. Then chi G is the sum of uth roots of unity. So chi G is an element of the field F zeta U, where zeta U is a primitive uth root of unity. And so this is an abelian extension of F. And this F chi, this is the standard notation that is followed, say, in Martin Isaac's book. This is the extension field of F by adjoining all the character values of G. And it is called the character field of this upper representation, rho tilde over F. Since F zeta U is an abelian Galois extension of F, it follows that F chi is also an abelian Galois extension field of F. So let A be the Galois group of F chi over F. It is easy to see that for each alpha, an element of A, the values alpha chi G are also values of a character of a representation of G over F, over F bar. So in effect, starting with rho tilde, we have obtained the cardinality of A, that many distinct representations of G over F bar. So any two of these representations are called algebraically conjugate. So this Galois group acts transitively on that. So in this way, we have obtained a class of mutually inequivalent algebraically conjugate representations of G. These representations have different characters, but they all have the same character field. So let Z1 denote this field F chi. So Z1 would be the Z in the previous discussion. So let E be the PCI, that is primitive central idempotent corresponding to rho tilde. Then E is in, of course, Z1G, the group algebra of G over Z1. And Z1G times E is a minimal two-sided ideal of Z1G. By the Witt-Berman Theorem, Z1GE is a matrix ring over a division algebra. Then the D1 to the N, that is the vector space which will be the representation space of G over Z1. So then Z1 is the center of D1 now, and the dimension of D1 over Z1 is M square for some M. So even if E1 is a maximal subfield of D1, it can serve as a splitting field for D1, and so the representation rho tilde is realizable over E1. So F bar may be of infinite dimensions over F, but we got something finite dimensional field E1, and the entries of matrices of rho tilde may be chosen to be in E. That is, we can choose a basis of the representation space V1 tensor E1 with respect to which all entries of the matrices rho tilde G for all G lie in E1. I think this discussion could be given in any standard course on representation theory. Our standard representation theory courses just deal with the algebraically closed case, whereas other fields are also important and in various contexts. So since a division algebra E1 over Z1, since this dimension is M and M is the least such dimension, we can take the second definition due to I. Reiner of Schur Index as the minimum of the dimensions of the fields E tilde over which the representation rho tilde is realizable over E tilde. So let V be the vector. You see this maximal subfield, they are not unique, not even up to isomorphism, but their dimensions are just M over the center. So let V be the vector space over F obtained from V1 by restriction of scalars from Z1 to F, and consider it as a representation space of a representation rho of G. Then it is easy to see that D1 is the centralizer of G in endomorphism ring of V, and the Schur index of rho, according to the first definition, Schur's way of thinking, equals to the Schur index of the representation of rho tilde, according to this modern definition. Now, let me define the F-conjugacy. It's a natural definition. Two elements, X and Y in G, are said to be F-conjugate if for all finite dimensional F representations of G, the representation rho of G, we have chi rho X equals chi rho Y. So when F is algebraically closed, this is the standard result in the algebraically closed case, that these irreducible characters are in one-to-one correspondence with the irreducible representations. Irreducible character means it cannot be written as a sum of two other non-trivial characters. So this is obviously an equivalence relation, and the F-conjugacy class of X consists of all those elements in G which are F conjugate to X. We denote the F-conjugacy class by CFX, and the usual conjugacy class, so to speak, absolute conjugacy class, which depend only on the group structure, by Cx. And it's clear that this is invariant under conjugation, and so the F-conjugacy class is an element of G, is a union of certain conjugacy classes. This much is information is clear from the definition. Now, Berman defined conjugacy in a different way. It's useful for actual computations, but it's more complicated. So let U be the least common multiple of the orders of elements of G. Let omega be the primitive uth root of unity in F bar, and let K be the Galois group of F omega over F, which is an abelian group. where homomorphism theta of the Galois group, this K is the Galois group of F omega over F, and this homomorphism from this to the unit group of Z mod U is defined as follows, that if sigma is in K, then sigma omega is omega to the A, where A is in Z star U. So these exponents, they are picked up. So, and we define theta sigma is equal to A. And let capital A be the image of theta under this homomorphism. We say that two elements of G are Berman conjugate if there exists G and a J in A, such that G inverse Xg is Y to the J, or that J in A. So, and one has to prove a theorem, it's not merely a remark, that X and Y are F conjugate if and only if they are Berman conjugate. Yeah, and so the F conjugacy classes are in one-to-one correspondence with F irreducible representations. Now, this is the essential arithmetic information that is needed in the theory. Let n be a positive integer, let F be a field of characteristic 0, etc., and let this be the decomposition of this cyclotomic polynomial into irreducible monic polynomials over F. So, if this can be done, then other things can be algorithmically defined. This is the point. And now this is an abelian extension of a simple kind, and the Galois arguments show that the degrees of all Fix are the same. And if choose one, say F1x, choose one of the factors, let zeta be one root, then other roots are the powers of these roots. So they are zeta to the R1, zeta to the R2, zeta to the Rs, where R1 is 1, and the sequence R1, R2, Rs is independent of the irreducible factors of phi and x and independent of the choice of zeta. So this 1, R2, R3, Rs, these are the terms which are occurring in that group A. So Witt-Berman theorem, if G is a finite group and F a field of characteristic 0 or prime to the order of G, then the number of inequivalent irreducible F representations of G is equal to the number of F conjugacy classes of elements of G. Okay. And now the F conjugacy class is just the union of the conjugacy class of X, X to the R2 up to X to the Rs. Yeah, and so this is also a serious theorem. So if you take the field to be R, then the Galois group is only Z mod 2, so X and X inverse. The conjugacy class of X union the conjugacy class of X inverse is the R conjugacy class of X. And let X be an element in G of order n, then the F conjugacy class of X is uniquely determined by the roots of just one irreducible factor, phi n x over F. So the F character table. So by the Witt-Berman theorem, the number of F conjugacy classes of elements of G is equal to the number of irreducible representations, and we can construct the F character table in the usual way. So the now you see the F this F character table is usually of a smaller size than the this absolute character table. So consider the important case when F is the rational and G is abelian, then the character table over F bar, if the order of G is n, so it's an n by n square matrix. And you see there is a lot of repetition. These are the algebraic conjugacy of these representations. On the other hand, if you factor G into product of primes, then the Q conjugacy class does not depend on the actual values of the primes at all, but they depend on only the way that the exponents, how they, the partitions of the exponent. This can be of a, the F character table is, in this case, very small. Okay, now the F-idempotents, we had defined the F-conjugacy classes, and this is the standard formula for idempotents when F is algebraically closed, and the same formula holds if instead of usual conjugacy class, you choose the F-conjugacy class. And now this n over the order of G, that n is the reduced dimension of the vector space. This n is a vector space over this division algebra D. It was a representation space over F first, then by this various other elements that are come into the game. So V becomes a vector space over that division algebra. And if that dimension is n, that is the reduced dimension of the of this representation. And so, this is the like the usual formula in the algebraically closed case. And one can read the complete set of PCIs from the F character table. Now, this is a beautiful theorem of Hermann. So, this is the crucial property about soluble groups that we use. We do not need to assume that the group is solvable in this case, that H is a normal subgroup of index P. And so G mod H is a cyclic group of order P. Let that be generated by X bar, and let X be a lift of X bar in G. So now this Berman's theorem is for algebraically closed case. So let F be an algebraically closed and semisimple case, and let C bar X be the conjugacy class sum of X in Fg. And then the C bar X is a central element in the group algebra of G. Now, G mod H is a cyclic group order P, and so this central element raised to the pth power is a central element in the group algebra of F. So, if eta is an irreducible F representation of H, and E eta is the PCI of eta. Now, there are two cases whether eta is conjugate to eta conjugated by X, eta is equivalent to eta conjugated by X or not. So, if it is not, then the direct sum is an irreducible representation of G. But now the crucial case is when eta is equivalent to eta sup X. Now, we are going to compute the PCI of this corresponding representation of G. Now, C bar x to the p e eta belongs to the center of f h e eta. Then, for algebraically closed field, by Schur's lemma, C bar x to the p e eta is a scalar, lambda e eta, where lambda is an f, and x in G minus h, that x can be chosen so that lambda is not 0. Now, let mu be any pth root of lambda, which exists because f is algebraically closed, and little c be C bar x e eta over mu. Then c to the p is exactly e eta, and then if you define this e sub x, x is an indeterminate, 1 plus x square plus x to the p minus 1 by p, and for this x, if you plug in theta I c, where I runs from 0 to p minus 1, then these are the these are p mutually orthogonal central idempotents in Fg. And after all, E eta can split into at most p idempotents. So these are actually, this is the decomposition into irreducible corresponding irreducible factors. And so each representation, eta extends in p distinct ways, just extends on the same vector space, which is the representation space of eta. This extra element little x in G minus h, it starts acting in p different ways, and it gives you the p extensions. And so in this case, and these idempotents are just E theta to the IC times E eta. So these are the idempotents that you obtained for the extended representation. So this is a nice observation for solvable group, that every irreducible representation of G is obtained by one-dimensional representations of an abelian subgroup by sequence of extensions and inductions. Now we want to generalize this in case F is not algebraically closed. Now you can see the kind of things, difficulties can arise, that that mu itself may not belong to F. That is one possibility. And the original representation eta over F may split into distinct representations over F bar. And so, that is the complication one has to deal with. So again, we have this information as before. And C bar x is again the conjugacy class sum of x in Fg. And let Z be the center of Fh E eta. Then the previous argument says that C bar x to the p E eta is lambda E eta, but now lambda is in Z. And lambda could be 0, and it may not have pth roots, and these are the issues. So we know by this Schur's theorem that we stated before that eta tensor F bar is M, this is the Schur index, times eta 1 tilde, eta 2 tilde, eta delta tilde, where delta is the dimension of that Z over F, and these eta are algebraically conjugate over F, and M is the Schur index. Let psi I tilde be the character of eta I tilde, and L, this F adjoined with the character values of psi I tilde. This is the common character field of all these eta I tilde over F. And let G be the Galois group of L over F. Then the order of G is equal to delta. And in terms of character, we can write psi is equal to this sum over these algebraically conjugate representations. And let D be the H-centraliser of eta, then D is a division ring. And in fact, the center of D is isomorphic to Z, which is a field. And if it tensors just with Z, then this M does not occur, but just the sum of the distinct mutually inequivalent irreducible Z representations of H. How many minutes? Over? Okay. So if eta sup x is itself not equivalent to eta, then as before, that is the simpler case. If it is equivalent to eta, then we have to see whether this E eta splits in a particular way or not. And I think let me just state the theorem. This lambda, we reduce to the case where lambda is not 0. And if lambda is no pth root, then that idempotent just continues. Idempotent of eta is an idempotent also in Fg. If it has two distinct pth roots, then it has all the pth roots. And then this idempotent will split into p idempotents. And otherwise, we shall have to see the factorization of the cyclotomic polynomial. And according to those factors, we have to sum these idempotents of E eta, and then we get the idempotent of G. Okay, then we also work out what is the induced representation, how it splits. There is another theorem on that. So the Schur indices are implicit here, but I think the essential algorithm can be best. We have not worked out that algorithm of writing down the actual matrices. But if we know the factorization of these cyclotomic polynomials, then we can work it out. And examples would have clarified much of this theory, but let that be for some other time. Thank you. Please do not tell me that you know all this, because there is a paper to be written. Yes. Yes. Yeah. Oh, can you? Yeah. That is this factorization of the cyclotomic polynomial. So if that factors into k factors, then cyclotomic polynomial, then the representation will split into 1 plus k factors. The factorization is over z, you keep that in mind. 1 plus k factors. Then you know this. So there will be one actual extension, and the others are kind of generalized extensions. All these are of the same degree, same dimensions over F. And from examples, you will be able to see that. Then, if it extends to an extends means what? The same vector space or some other vector space? There will be only one vector space, only one representation which actually extends. And the others, they do not extend. They are generalized extensions. One has to define generalized extension. That E eta will split into corresponding to the factor x minus 1 of x to the p minus 1. So E eta multiplied by something. Now, that we are not considered. We just second theorem will give actually the decomposition of the induced representation. That also depends on this factorization of the cyclotomic polynomial. Yeah.